This first section in chapter 2 is really just introducing the idea of force. And the question that we really ask ourselves, having completed chapter 1, is how exactly do you go about changing momentum? And if we went ahead and did some experiments, we would find out that it depends on how hard you push on it, in other words, the force, and how long you push on it. So we see that the rate of which momentum changes depends on the force. Now, just to remind you, the equation for delta P, change in momentum, is just P final minus P initial. And so the chapter then kind of goes on to talk about what is a force, how do we measure a force, and one of the ideas that you're really going to want to understand is the concept of net force. And by net force, we simply mean what's the total force. So let's say we have an apple that is sitting on a table. And we'd like to know what exactly is the net force acting on that apple. And we'll go about doing that by drawing what we call a free body diagram. It's called a free body diagram because we take away all other information except for the object itself. And then we look at the forces that are exerted on that object by other things. So our free body diagram for the apple, first thing, we represent the object with just a dot. Just a simplified thing, we're treating the object as a single point. And then we go ahead and we draw arrows representing the different forces pushing on this. So clearly the thing's sitting on a table. So we have a force on the apple by the table. And of course gravity's pulling down, so we've got another force down like this. This is a force on the apple by the earth. And that's really the only forces on there. This is our free body diagram. And so the net force is just the sum of those two. So F net on the apple is just F on apple by table plus F on apple by earth. And we could also go ahead and add these two up graphically. Now, we know that the apple is stationary. That means that for this apple, delta P is equal to 0. Since delta P is equal to 0, that tells us something about what the net force has to be. If we go back to this equation right here, we can see the relationship. Delta P is F net delta T. Now that apple's going to be sitting there for a long time, so this delta T could be however long it sits there, a few seconds. So the only way for delta P to be 0 is if our net force is also 0. So delta P being equal to 0 implies that F net is also equal to 0. So that kind of gives us some information, and then these two arrows here should graphically add up to 0. And hopefully you remember how to do this. To add up two arrows, we place them nose to tail. So let me draw the first one. Let me draw the F on apple by table, which started right here, and then draw F on apple by earth, which is going to go back down like this. And the sum of those two is from the tail of the first to the nose of the last, which is just a dot. In other words, these two vectors add up to 0. So if we just consider one other situation, what would happen if the apple wasn't sitting on the table? What if the apple was falling? Well, for the falling apple, really there's only two forces that we need to consider. The first is the same one that we had before, F on apple by earth. And then a very tiny, tiny, tiny force up, which is F on apple by air. And so the net force is just going to be the sum of these two. You've got a large downward force, a small upward force. So in this case, F net is going to be downward and just a little bit smaller than this. This would be my F net. That tells us then that the momentum has to be changing. As this thing falls, this momentum, as delta P, is going to get bigger and bigger and bigger.